So now that we're done with that last example problem, we're going to go ahead and solve exercise 7. In The Little Prince, the prince visits a small asteroid called B612. If asteroid B612 has a radius of only 20 meters and a mass of 1 times 10 to the 4th kilograms, what is the acceleration due to gravity on asteroid B612? So here's B612, and the radius of it is 20 meters. The mass that we're given is 1 times 10 to the 4th kilograms. And our equation is the acceleration due to gravity on B612 is going to equal the mass of B612 times the gravitational force constant divided by the distance between them squared, which the distance is the radius of B612. Previously, I had written this equation, and your textbook did also, like that. Same thing, those two equations. Just swap these around. Anyway, so let's plug them in. Here is my calculator. Let's use this equation. Just forget that one for now. The mass is 1 times 10 to the 4th kilograms. 1 10 to the 4th times the the gravitational force constant, 6.67, shift 10 to the negative 11, and divided by the radius squared, which the radius is 20 meters, divided by 20 meters squared. The value that I'm getting for that is 1.6675 times 10 to the negative 9th. Let's take this opportunity to talk about significant digits. So again, the value I got, answer, is 1.6675 10 to the negative 9th. And that should be in meters per second squared. Now, here's the deal. Let's talk significant digits for a second. The numbers that they gave us to work with were 20 meters to the first decimal place and 1.00. This factor here, 10 to the 4th, is just a placeholder. It's nothing more than that. There's no significant measurement that's going on in that. But if we were talking that this were something like a pile of salt, 1 times 10 to the 4th kilograms of a pile of salt. So let's say there's my pile of salt. And it was 1.00 times 10 to the 4th kilograms. The level of accuracy at which they measured this salt is to that decimal place right there. Another way that you could write this is 1.00001234 kilograms. So they didn't measure it any more accurate than that value right there. You know that it's not less than this. It's not 9999. It's not this. It's not that. They measured it no more accurately than that. What does that also mean? It means it's not 10,000.0. We didn't measure it to that accuracy. So why is this important? Well, when you're doing this problem and other problems like it, you're given all of these numbers, right, in your answer. Do I need to write these down? The answer is no, you should not, because you multiplied with 20.0 and 1.00 times 10 to the 4th. The level of accuracy in this problem is limited to that decimal place and to these decimal places. How do we show that level of accuracy in our answer? Well, there's 1, 2, 3 significant digits in this factor that we use math with, and there's 3 significant digits in that factor we used math with. So we're going to limit our significant digits to 3, the minimum amount of significant digits that we multiplied or divided with in this case. So let's round this to 1.7 times 10 to the negative 9th. Excuse me, 1.77 times 10 to the negative 9th. Units. To keep this video short, I'm not going to show you how to get the units for this problem. Just remember that as long as you're using the meters per second squared and your other factors, so meters were in this one, kilograms were here, and the gravitational force constant has Newton meter squared over kilogram squared. The seconds that we got for this, the second squared, came out of newtons. They're up in there. So as long as you did that math correct, those units are going to be there. For purposes of ending this video, I'm not going to show you how to get those right now.